Hello friends, welcome to Dr. Sai Physiology Academy, DOPA for short. This is the place where we make the learning of physiology easy, exciting, and effective. Thank you for joining me. And if you're new to this channel, you're especially welcome. And if you love the content that we share, kindly click the like button and also the subscribe button. And don't forget to turn on notifications so you don't get to miss any new content that we drop. Now let's get started. So today we are dealing with membrane potentials. All right? It has to do with electricity, all about electricity, but in the biological system. Now, the discovery of electricity and its practical application in technology, in fact, it marked a major revolution in the world. Electricity. Now, just take a look. Every piece of technology that you use, okay, check it. You see that it's dependent on electricity. Now in this room where I'm doing this video recording now, the light, what is making it come on, shine? Electricity is powering it, converting electricity to light energy, electrical energy to light energy. In this room also, we have the AC, air conditioner. It uses electricity. I have a standing fan here. It uses electricity. My phones, it uses a battery. Okay, the phones, they use a battery, which actually it's called a dry cell. It's giving out electricity. It's powering the phone. Okay, then when it goes down, you need to charge the battery. You plug it to electric source. The camcorder I'm using to record, what happens? It has a battery that powers the camcorder. Electricity, all the components there, they function through electricity. And when the battery is also down, I charge it. This microphone here is connected to a battery in my pocket. There's a battery there that's powering everything. Electricity, your laptop, your refrigerator, your everything, your TV. That's why I say it marked a revolution. Why? Because electrical energy, it's like the universal form of energy that you can easily convert other forms of energy into it, and you can easily convert electrical energy to other forms of energy. That's what technology is all about. So but the body has already done that a long time ago. Your ability to hear, to see, to taste, to move your hand, everything depends on electrical impulses. You understand that? That's why it's very important. Now look at this. One of the ways in which electricity can be generated, they have different ways in which you can generate electricity, is chemical energy. And your body is made up of chemicals. Basically, the food you eat, they're all chemicals. Your blood, everything is chemicals. So the way the body generates electricity is through chemical energy. You know what they call, you have a dry cell, and you have wet cell. Abi, from your chemistry or physics. So all this battery you put in your wall clock is dry cell. It generates electricity. Then you have the wet cell, the one you use in your, like the car battery. There's liquid inside. It's form of a solution that generates electrical current. All right. So the nerve is like a wet cell. It has the ability to generate electricity through chemicals that surround it. Every cell is bathed by extracellular fluid that has what? Chemicals and ions. So when you talk about wet cell, chemical energy to electrical energy, you're just talking about the fact that in solution like this, you have charges, positive ions, negative ions distributed. And there's what is known as potential difference, which is actually the difference in the magnitude of these two charges, negative, positive. The difference between them is called the potential difference, and it's measured in potential. Let me write it here. Potential difference. From your physics, you've learned some principles of electricity, so this should be straightforward. I'm just linking the two. Potential difference is measured in what? Volts. But because in the living system in your body, it's actually very small, the charges are very little, so we actually now measure them in millivolts. MV for short. Okay, so you have ions, you have electrolytes in your body: sodium ion, potassium ion, calcium ion, and so on and so forth, phosphate ions, all of that in the extracellular and the intracellular fluid. So what happens is that, we are dealing with excitable tissues. Excitable cells are cells that they have a large potential difference that exists. Now there are 2 points that we reference points. Now this is like a cell, okay, the nucleus. Then extracellular fluid here, like this, is surrounding it. It has intracellular fluid. So what happens is that the charges that are close to the membrane are dealing with membrane potentials. Okay, the charges that are close to the membrane, they align themselves to the membrane. This one also outside, they align themselves close to this membrane. They are concentrated more, okay, at the membrane. So it's called separation of charges. Okay, separation of charges, they are aligned there. So what happens is that there is a difference in the magnitude of charge that is inside the cell, the edge of it inside, and the magnitude of charge that is outside. Okay, so it generates a potential difference which is known as the membrane potential. So when this cell, more specifically now the nerve cell, when it's not doing anything, the charges, they are not flowing, when it's at rest, it is known as the resting membrane potential. Okay, that is not being propagated. No electrical current flows. So when it's not flowing, it's just there, stagnant, not doing any work, not performing any action. It is known as the resting membrane potential. I don't know if you understand this. Okay, so the next thing we're going to be dealing with is how. Physiology has to do with mechanisms. How is the resting membrane potential generated? Okay, under membrane potentials, we have resting membrane potential and action potential. I'm going to be dealing with that in the part 2. But now we are focusing on resting membrane potential. So after this break, we're going to be really going into details of how is the membrane potential of the nerve cell or muscle cell applies to excitability. How are they generated? Don't go anywhere after this break. All right, you're welcome back. So now we want to now deal with how this resting membrane potential, how is it generated, number one, and how is it maintained? How is it established in the first place? All right, so now one, okay, we're going to be dealing with how it's generated and how it's maintained. So under this generation, there are 2 things that are involved. A, you have the contribution of ion concentration gradients. I will explain all of that to you. Okay, then B, contribution of ion permeabilities. All right, talk about the maintainer. So what do we mean by this? Now, to understand this, there are 2 major ions that we are going to be focusing on because they contribute the most. They are the most significant, okay, in dealing with anything membrane potentials, including resting membrane and action potential, okay? And they are sodium and potassium. Those two, sodium and potassium. And now, what do we mean by contribution of ion concentration gradient? Now, let me draw two cells. 1, 2. So we're going to be assuming that this cell is just all about sodium. This cell is just all about potassium. Now, naturally, potassium is high intracellularly, very high intracellular compared to its extracellular concentration. Why potassium? So this one is let's put this one as sodium. Sodium is very high outside. Actually, it's about 135 to 145. So let's just put it 140 millimoles per liter. Okay, that's the concentration of sodium outside. Then inside it's low, very low. Sodium is low inside. Its concentration inside is around 12 millimole per liter. Okay, so this one now, let's go to potassium. Potassium is high inside and low outside. Inside, potassium is high. And what is that? It has about 150 millimoles per liter inside. Then outside, it has just about 5 millimole per liter inside. So outside is low potassium. Okay, so we are dealing with them differently now to understand their contribution to the membrane potential. Now, so what do you think will happen now? This one is low inside here, 150 and 5 millimoles. So there is a very large difference. Okay, a very large difference. So what do you think will happen? There will be a tendency for potassium to want to move along its concentration gradient, which is from inside to outside. Do you understand that? Okay, potassium, remember that it's a positive ion. So the concentration gradient is trying to push potassium from inside to outside. But so as potassium is trying to want to go outside, what do you think will happen? As it's going outside, here is becoming more positive. We are assuming that this is just all about potassium, okay? Here is becoming more positive, here is becoming less positive, inside is becoming less, but as potassium is moving. So as here is becoming more positive, it is repelling the charge because there are two forces. Let me write it down here. Two forces. Okay, these two forces, one of them is the electrical force, then the second one is the chemical force. So you have the chemical gradient, or also known as concentration gradient, that is trying to push sodium from inside out, okay, because it's higher here. So as it's going out, it's now increasing the electrical positivity outside. And you know that positive charges, they repel each other. So as more positive is going outside, it's repelling and going against, resisting further movement. So as more and more positive is going out, it will get to a point that the positive here is now high enough to stop further movement of potassium. So there's now a balance between the concentration gradient, the force of the concentration gradient, which is from inside out, while the electrical gradient is now pushing it from outside in, because positivity is increasing inside, so it's repelling it. Okay, so it gets to a point where the force, the electrical force, trying to resist and repel it back inside, and the concentration gradient force, okay, that's trying to push it outside, at a point they become equal. Okay, that is called the equilibrium potential for potassium. So, and that happens at about minus 90 millivolts. Minus 90 millivolts. Now, what are we talking about here? We're trying to say that because sodium, potassium is moving from inside out, we are referring to it as minus. Okay, the reference point is inside, so moving from inside out, it's minus. Just take it like that. Okay, then moving from outside in is plus. Do you understand that? So at minus 90 they reach equilibrium. Remember, we are just dealing with only potassium. So this is the equilibrium potential for potassium. So coming to sodium, exactly the same thing happens. Okay, so sodium, the concentration is trying to go in, okay, because it's much outside, it's trying to go in, but to get to a point where the positivity, the positive charge inside is now increasing, and increases enough to resist further influx of sodium into. So at that point, it's known as the equilibrium potential for sodium. And because sodium is coming from outside in, its own is plus. So it's about plus 60 millivolts. Do you understand it now? Okay, it's an interplay of force of concentration gradient and the force of electrical gradient that are opposing each other. So they get to a point where there's now balance, equilibrium, known as equilibrium potential. Now you have minus 90 by potassium plus 60 by sodium. Now let's now put them together in one cell. That leads us to what? The contribution of ion permeabilities. It now happens that in a cell, there's what is known as leak channels. Leak channels. Leak channels. So you have leak channels for potassium, you have leak channels for sodium. But it now happens that potassium leak channels are far more than sodium leak channels. Do you understand that? So more potassium tends to leave the cell. No, it's high inside. So more potassium tends to leave the cell than sodium is entering the cell. No, we have put them together. We also want to establish the equilibrium potential. That's why we assume that it's just only potassium that is existing, only this existing. Now, so now is the leak channels we're now focusing on, the permeabilities. So the cell membrane is far more permeable to potassium because of numerous leak channels than it is to sodium. So what do you think will result? It will result in the fact that potassium will contribute more to the membrane potential than sodium. Do you understand that? So the overall resting membrane potential of the cell is closer to the equilibrium potential of potassium, and it is usually around minus 70 millivolts. You see that this positivity plus 60 of sodium is what will I say diluted it from minus 90 to minus 70. But because potassium is far more, that's the leak channels, that's why it is closer. So in essence, potassium contributes the most to the value of the resting membrane potential. So in a nerve cell like this, a typical nerve cell, the resting membrane potential is around minus 70 millivolts because mainly of potassium, because of the numerous leak channels. Do you understand that? So this equilibrium potential contribution of the ionic gradients has helped us to understand the equilibrium potential of individual ions, sodium and potassium, and then the permeabilities has now helped us to understand the final resting membrane potential being closer to the equilibrium potential of potassium because of the numerous leak channels. Do you understand that now? So that is it. So the next thing I'm going to be talking about is how is it now maintained? How is it maintained? There is what is known as what? The sodium potassium ATPase. This particular enzyme is present in every cell, every single cell, because apart from its contribution to development of membrane potential, it also contributes to the normal functioning of cell. Usually that's to do with transportation across the cell membrane. We dealt with that in general physiology. All right, secondary active transport. You see that sodium plays a lot of role because of this particular enzyme or pump, because it uses energy, ATP. Okay, so this particular pump plays a role in the sense that it pumps out 3 molecules of sodium to the exterior, okay, to the extracellular fluid, and pumps in 2 molecules of potassium into the cell. Do you understand that now? Against that concentration gradient, sodium is already high outside, but it's still pumping 3 out, pumping 2 molecules of potassium inside. So that in itself helps to maintain the resting membrane potential. So but its contribution to it is just about minus 3 to 4 millivolts. Okay, its contribution to the overall resting membrane potential is little. It's just there to maintain it. All right, so this is what happens. Resting membrane potential. So the next thing we're going to be dealing in the next lecture is action potential. That one is very interesting and you need to really understand it. So I'm going to see you in the next video.